Okay, we are going through 9.7, 9.10, worksheet 2. This is the back page here. Number 3, let f be the function given by f of x equals e to the negative 2x squared. Find the first four non-zero terms and the general term. Okay, so we don't want to forget to create our general term after our first four non-zero terms. About x equals 0, so we're dealing with Maclaurin series. Okay, so we can build this from something that we know. This is kind of coming from the parent graph e to the x, or the parent series e to the x, and we know the series for e to the x first four terms is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And so from here we can build e to the negative 2x squared by replacing our exponent of x with negative 2x squared. So that means in our polynomial we can replace every x we see with negative 2x squared. So negative 2x squared replaces the first x, replaces the second x, replaces the third x, and then if we try to clean this up a little bit, we can see the pattern here. 4 is the same thing as 2 squared, and 8 is the same thing as 2 cubed. And now we can look to see how we can build our general term. First off, we know that there's going to be an alternator since each term is going to be changing signs, so we have the negative 1 to the n. We also see that the coefficients is going up by factors of 2, so we can have a 2 to the n representing that. And then the exponent for the x is going to be it's going to be 1 ahead, or factors of 2, but it'll be 1 ahead of the exponent for the base 2. So this is 2 squared, but it's x to the 4th, cubed, but x to the 6th. So we can think of it as 2n, right? And then we know the denominator will match the degree of the exponent for the base, so n factorial. So now we just have to test this out, right? If we start off with n equals 0, so n equals 0, all this will be just reduced to be 1. Second term will be 1, so that will make this negative 2 to the first times x squared over 1, so that matches the second term. Third term would be n equals 2, so 2 squared, x to the 4th over 2 factorial, that matches. And then if I have 3, this term will be negative 2 cubed, matches, x to the 6th, because 2 times 3 is 6, 3 factorial, that matches as well. So we've confirmed that the general term that we created matches the first four terms of our series. Part B, find the interval of convergence for the power series about x equals 0. So if we're trying to determine convergence for power series, we usually go through a ratio test. So limit as n approaches infinity for a sub n plus 1. So replace every n we see with n plus 1. Okay, divided by a sub n, which is the same thing as multiplying by the reciprocal. And if we try to clean this up a bit, 2 to the n will cancel out, leaving us with just 2. X to the 2n plus 2 will give us will cancel out with x to the 2n. With the only thing remaining is x squared. And then n factorial over n plus 1 factorial reduces to be just n plus 1. If we do limit as n approaches infinity, x is just a constant. It'll stay a constant. But n approaching infinity, it'll cause the denominator to grow larger and larger until this expression, this fraction, will go to 0. And if it goes to 0, then that's always going to be less than 1. If it's always less than 1, then that means for all x, our interval of convergence is going to be all real numbers. So that means for all x, this series will converge. Part C, let g be the function given by the sum of the first four non-zero terms of the power series, and show that the absolute value of f of x minus g of x is less than 0.02. Okay, so if we think about the alternating series remainder, then we know that the most that the series will be off by will be less than the first unused term. So we're trying to find the sum of the first four non-zero terms, so that means the fifth term will tell us at most how much our approximation of the first four terms is off of the actual value. of the series. So we know here we have the first 4 non-zero terms. So that means the fifth term will determine. So the fifth term would have to be 2 to the fourth, x to the seventh over x to the eighth, sorry, over 4 factorial. So that's exactly what the fifth term is. So if we reduce the fifth term, it'll be 16x to the eighth over 24, which 16 over 24 reduced to be 2/3 x to the eighth. So we want to maximize these values because we want to know what the maximum error could be. So 2/3 x to the eighth will reach its maximum value between negative 0.6 and 0.6 at these endpoints as well. All right, these endpoints, the absolute value of these endpoints will produce the largest value that that any x could be. So we know 2/3 x to the eighth is going to be maximized at the endpoints because any value that we plug in between negative 0.6 and 0.6 will not cause this to be any greater value, or at least the absolute value won't be any greater. So the maximum value is going to be created at 2/3, absolute value of 2/3, 0.6 to the eighth. If we use our calculator, is 0.01197, which we know that whatever the maximum error is, this value will be less than 0.02. Okay, Maclaurin series is given. Find f prime of 0 and the 17th derivative at x equals 0. So if we think about using the Taylor series, it's going to be, if I want to find f prime of 0, then f prime of 0, it's just going to be the value that's in front here. So the coefficient rather. So f prime 0 over 1 factorial. So f prime of 0, if we want to find the derivative of each of the terms and then plug in 0 for the remaining term, the first derivative will produce 1/2. And if I replace everything else with 0, then my coefficient will be 1/2. Okay. And then if I plug in 0 into that in for the x, I get 1/2 as the coefficient of for f prime, or the value for f prime. Okay, the 17th derivative evaluated at 0 is going to be dealing with the x to the 17th over 18 factorial. Okay, and if we find the derivative of this all the way down to the 17th derivative, then it'll be 17 x to the 16th, and then each of the terms will cancel out all the way down until we're left with 17 over x to the 17th over 18 factorial. Okay, and then 18 factorial, if we plug in 0 in for x, we get 1 over 18. Okay, part B, for what value of x does the series converge? So we're dealing with this series here, so we can go through ratio test. So we add 1 to do a sub n plus 1 divided by a sub n. So here's a sub n plus 1 divided by a sub n, which is multiplied by the reciprocal. And we see that the x to the n's essentially cancels out, leaving us with just x. N plus 1 factorial, n plus 2 factorial reduced to be just n plus 2 in the denominator. And if we evaluate the limit as n approaches infinity, remember x is just a number that will stay as that number, but n is going to be increasing to infinity, so that will cause this fraction to go to 0. If it's 0, then that means our interval convergence is that this series will converge for all real numbers from negative to positive infinity. Okay, part C. Let g of x be x times f of x. So here we have f of x here, right? We have the first 4 terms here. Write the Maclaurin series as in terms of a familiar function, or a function that we can recognize without using series. So this is what g of x looks like. G of x, it will be x times f of x. So we can write out the first few terms of f of x. So here's the first few terms of f of x with the x out in front. If I distribute through, let's see if we can recognize the series here. So we get x plus x squared over 2 factorial plus x cubed over 3 factorial plus x fourth to 4 factorial. Now if we look, this looks a lot like e to the x, the first few terms of e to the x. But e to the x starts off with a plus 1 in front. So really, this is essentially e to the x without the 1 in front. So we know that this, we can then think of this as e to the x minus 1. If I do e to the x minus, if I take away the 1 from e to the x, then this is the series that I'm going to get. So we can replace, we know that g of x is x times f of x, and we know g of x is therefore e to the x minus 1. If g of x is e to the x minus 1, we can then solve for f of x by dividing the x over. So f of x is essentially e to the x minus 1 over x.